So the first thing I want to go over in this multi-step theme lesson is some information about reactions that you must know. It is an expectation of the curriculum that you are familiar with photosynthesis, cellular respiration, and how that relates to open and closed combustion. So I've put up the reaction for photosynthesis. It is just the opposite of a combustion reaction. So you shouldn't think of this as something totally new. You're actually making the fuel, and it's a sugar. You make oxygen, and you start with water and CO2. Okay? Again, total opposite of a combustion reaction. One big thing I want to highlight that in photosynthesis, or anything that happens inside a cell, the state of the water is liquid. Okay? Now, where that affects us in this unit is that liquid water and gaseous water have different molar enthalpy values. Okay? Cellular respiration is really just a combustion reaction. It's the opposite of photosynthesis. Okay? This is the one that students probably should memorize or make sure they know. The fuel is your sugar. It's going to react with oxygen. It's going to make carbon dioxide, and because it's inside a cell, it's going to make liquid water. So these are fair game reactions for tests, quizzes, and or diploma exams if they were being written. Okay. I want to compare that to combustion, and this is something that is often tied in test questions. Okay. And when I'm talking about combustion, I'm referring to open combustion. This would be like we do in labs. You combust methanol or ethanol in a flame. You burn some fuel with a candle open to the atmosphere. Very similar reaction to cellular respiration, except for you get water vapor. Okay. So just make sure you know about photosynthesis, you know about cellular respiration, and you can compare or contrast it to combustion, which is open, and you get the vapor product. Next, I'm going to roll in and do two multi-step examples. In our first example, we're going to talk about the fuel that is used in many rockets today. Okay. Now, this is not the fuel used by SpaceX, but many other rocket companies use hydrogen-oxygen fuels. Okay. And we're going to be talking about a hydrogen-oxygen reaction. Okay. We're going to look at a hydrogen-oxygen reaction where 27 grams of water vapor are produced. And we're going to solve, what if all that heat that was produced went into a 10.3 kilogram block of aluminum? What would the temperature increase be of that block of aluminum? Okay. So this is definitely a multi-step problem. When you get a multi-step question like this, your ultimate strategy is to get molar enthalpy and then use that molar enthalpy to solve your problem. So I'm going to set this up a little bit in the middle or towards the end and work backwards. Okay. Okay. To solve for the actual combustion, of our 27 grams, we can figure out how much heat that released if we know how many moles we have and we know the molar enthalpy. Okay. But we can't get started there because we've got to get the molar enthalpy first, and that's what kind of makes these multi-step. Okay. We've got to take what information is given and get our molar enthalpy, and then we can do this bottom calculation reasonably quickly. So I'm going to scan the question for any signs of information that I can use to get molar enthalpy, and I have nothing. I have no calorimetry data. I wasn't told how much energy was released per mole, so I'm going to have to use my data booklet to predict it. Okay? If I know the balanced chemical equation, I can look up the formation values of the products and the reactants. So I need an equation. So I have hydrogen gas plus oxygen gas, and that is going to make water vapor. It's not a hydrocarbon combustion, but it is an open combustion. I'm going to need to balance this. Oxygen isn't balanced. I can double my water to balance my O, and then I have to put a 2 in front of my hydrogen fuel. Okay. And our data booklet lets us look up values to predict this reaction. Okay. When we predict it, it'll always be under standard conditions. Now, I picked this particular example. It's going to be a bit easier because if we think of molar formation values, this is a formation reaction. So the hydrogen formation value will be 0. The oxygen formation value will be 0. The formation value for water is 241.8 kilojoules per mole. So I've made this one a little bit easier to solve because of the fact we started from 2 elements, which are 0. Okay. And we actually really don't even have to calculate our molar enthalpy of formation. We have it right there in the blue number. Okay. I'm going to complete this process and calculate it, and we'll see we're just going to end up with that green number. Okay. If I wanted to get the delta H for the reaction, well, I know the molar enthalpy. I know there's 2 moles. Okay. So if I take 2 moles times minus 241.8 kilojoules per mole, this reaction would have a change in enthalpy of minus 483.6 kilojoules. I can get the molar enthalpy for water, which I kind of already know. Well, that would be the 483.6 kilojoules divided by the fact that there's 2 moles in this reaction. Okay. What I just did in red is something you'll have to do if it didn't happen to be a formation reaction. You'd have to solve for the delta H and then divide it by the number of moles. So ultimately, you need to find, in a multi-step question, some data that lets you figure out what the change in enthalpy is, the molar change in enthalpy. We predicted it, and now we're going to use it to solve not how much energy is released when 2 moles react, like our question shows. Okay, we know 2 full moles is minus 483.6 kilojoules. We want to know if 27 grams react. So if I have 27 grams reacting divided by the molar mass of water, 18.02 grams per mole. Just checking, I have 27.0 up in the question, so I'm adding that 0 in, okay? And I multiply that by our molar enthalpy, 241.8 kilojoules per mole. Okay? Now, often I separate out the mole calculation on the side. I just put it all together in this case. So we end up with about 1.5 grams. When you take the 27 and divide by 18, that's about 1.5. So we end up with 1.5 times the energy. So our change in enthalpy when 27 grams react is 362 kilojoules released. That's how much energy is going to go into that aluminum block. And then finally, I have to deal with, well, what temperature change is that going to cause in the aluminum block? Okay. Anytime you're told of a temperature changes, the only strategy technique we have to use is Q is mc delta T. The heat that went into some material is equal to the mass of that material, the specific heat capacity of that material times the delta T of that material. Okay. And we're asked for the delta T, so we need to know everything else, and we do have all that information. If we think of what is the Q, how much heat went into the aluminum block, that's what we just solved for. Okay. Okay. Delta H is a vector. Okay. Delta H tells us the change in energy and the direction that it goes in. Q is a scalar. It just tells us how much heat flows, but it doesn't have that arrow or direction to it. It doesn't have the positive or the minus. But conceptually, change in enthalpy and Q are both relating to the movement of thermal energy or heat. Okay, Q specifically is called heat, where delta H is change in enthalpy. Okay, so this number is our Q value. Okay. Now I'm just going to change my units a bit. I know the C value is in joules. Okay. So I'm going to do this whole calculation in joules to watch my units. So this is 362,000 joules is how much heat went into the aluminum block. The mass of our aluminum block is 10.3 kilograms, 10.3 thousand grams. So 10,300 grams. Okay. Again, I'm basing all my units off. C is joules per gram per degree Celsius. So I'm making sure I'm using joules throughout the calculation, and I'm making sure I use grams, and that will output degrees Celsius. Okay. Now I need the specific heat of aluminum. We're so used to water. Now I've included a little piece of page 3 of your data table, all the specific heat capacities that are given to you, and the C for aluminum is a little under 0.9, 0.897 joules per gram per degree Celsius. And last, we have our unknown delta T. So now I can rearrange and solve for this. So our change in temperature of our aluminum block, we're at the end of this question finally, is the energy that was put into the aluminum divided by the mass in grams of that aluminum divided by a specific heat capacity. Now I said the word divided by and then wrote multiply. The 0.897 is a denominator in this. So when I put this into my calculator, I'm not going to use any brackets. I put the numerator into my calculator, and then I went divide by the mass and then divide by the specific heat capacity. Okay. I've been careful, so all my units are going to line up. Joules and joules, grams and grams. I'm left with degrees Celsius on the bottom of the bottom, inverse twice. So I just have degrees Celsius, and I got 39.2 degrees Celsius as my change in temperature. Okay. Now I did strip out the minus when I went from change in enthalpy, which has a minus, to Q, which is a scalar. I didn't put the sign in, but that sign means energy was released, so this temperature is an increase. as released energy would increase the temperature. So this is a pretty long multi-step. There's lots of workbook questions and practice that you have to do that might be this long. It's a little long for a test or quiz. Okay. So that's my first example of a multi-step style question. I'm going to do one more. This is going to be a multi-step question, but it's going to be much shorter. Okay. 5 grams of butane was combusted, and a 250,000-ish joules of energy was released. Okay. And we're wondering what the molar enthalpy of butane is under these conditions. Okay. Well, molar enthalpy is normally our middle step. In this case, it is going to be our final step. We don't have to do anything else with it. We just want to get molar enthalpy of the combustion of butane. So I'm using the proper notation for molar enthalpy. I'm not putting in that little not symbol because we're not told anything that we're under standard conditions. And I wouldn't want to write a balanced chemical equation and use my data booklet, because there's no reason to start trying to predict enthalpy changes when we're given data. Okay. And again, that's very important on a test or quiz, that you don't start trying to predict, use formation values when you have energies. Okay. In the previous question, we had no energies given, we had to predict them. Here, we know the change in enthalpy, okay? And we know a corresponding amount of chemical that reacted. So we're going to be able to calculate this right away. So just correcting, butane is C4H10. Okay. Now, what's key is that you have a linked delta H and a linked moles, and we have this. We know that this amount of energy, that 250,000 joules, corresponds to the 5 grams. Okay? They are from the same situation, so I can use both of these together. Okay? So we have 251,200 joules. I'm just going to convert that to kilojoules, because that's the most common unit you'll see when we output molar enthalpies, and your testing quizzes will ask you for kilojoule units. Okay, so I divided our joules by 1,000 to get into kilojoules. Okay, but there's our energy release there. That's what we need to get to build delta H. I just have to add in the right sign. Okay. Now this is a combustion reaction, so that would tell me for sure this is going to be exothermic, that energy is going to be released. And right in the question, it's telling you again, reinforcing that energy is released. So this is a minus. That's a minus 251.2 kilojoules as a delta H. Okay. Now I just need the moles. Moles for our butane, C4H10, is mass over molar mass. Okay. This is not a solution. It is a pure substance. The mass of 4 carbons and 10 hydrogens is 58.14 grams per mole. And that gives us 0.0860 moles. Okay. Now I'm rounding values to put them on my smartboard. You should, and I have been keeping all the digits in my calculator and only rounding at the end. Okay? But I'm not going to write every digit in my calculator on the board. Okay? So that's our moles. Okay. So a much quicker question. We got the delta H quickly, we got the moles quickly, so the molar enthalpy. I like to write that minus right away so I don't forget, minus 2,920 kilojoules per mole combusted. Okay. I have rounded my answer to 3 significant figures because the mass, which led to my moles, only had 3 measured digits, so that was limiting how many sig figs I would have in this question. Okay. Our other piece of information had 4 significant figures, 3 being the lower. Okay. This would be a very typical standard question that you would have on a test or quiz. Okay? And we would hope that with practice, this is something you could solve relatively quickly, particularly by the time you get to the unit test. Okay. So that's my 2 multi-step examples I wanted to go over. A couple other quick things just to recap or introduce. One is a slight variation on calorimetry referred to as bomb calorimetry. Okay. You're not likely to see many questions like this. There is one in your workbook. Question number 7 in your workbook is a bomb calorimetry type question. In bomb calorimetry, the little m and the little c are put together. Okay? And that is referred to as heat capacity. Okay? When they're separated out, the little c is specific heat capacity. So Q is MC delta T. That's what you're used to. For that, C is specific heat capacity. Okay. In bomb calorimetry, we have a whole bunch of materials that the heat is going into. Okay. And you have to figure out what is the heat capacity of all of those materials lumped together. And each instrument, each bomb calorimeter would have its own value. Okay? A bomb calorimeter is often a 1-inch thick piece of steel or a steel sphere, and you put your chemical reactant inside that sphere and literally blow up or combust whatever material you want to analyze with very high concentrations of oxygen. You get as close to complete combustion as you can, and all that heat goes into that surrounding metal and potentially metal and water. Okay. So in bomb calorimetry, you just have big Q equals the M and the C have been combined into just one big C value, and then you still have the delta T. So it's actually a little bit easier to solve a bomb calorimetry question. Okay. Your M and your C, your material, the mass of whatever material is your surroundings, and the C are just combined. In Chem 30, we tend to focus on using the heat going into just one material as opposed to a combination of materials. Okay. Last thing, I just want to clarify or give you a little more information on chemical potential energy diagrams, in particular preparing you for upcoming assessment. So the responding variable, the y-axis is potential energy. Our x-axis is reaction coordinate. I'm going to put some more numbers in here to prepare you for potentially answering questions. We always start with the reactants, whatever they might be. And let's say the reactants are starting at 100 kilojoules. I'll just label my units of potential energy. Okay. And a reaction progresses, and we have some products, and those products are sitting at 175 kilojoules. Okay. And I'm going to answer and talk about a few quantities in a second. As this reaction progresses, the potential energy doesn't just go straight from reactants to products. As a reaction progresses, we have to put some energy in to get the chemicals to break up. So we have a shoot up in potential energy. We'll talk a lot about this later in the unit. This would be an example of putting a spark into a fuel, putting some extra energy in to get the reaction to start. And because we're putting energy in to get the reaction to start, we see potential energy rising. Okay, we get to the maximum potential energy, and then the chemicals go in and start forming our new products. Okay. And a diagram like this leads to a lot of potential questions that could be asked. Okay, we could ask you for the potential energy of the reactants, potential energy of the products, or even more likely, what is the enthalpy change? Okay. And the enthalpy change is the difference between, where you started and where you finished. And we've been drawing that as change in enthalpy arrows. Okay. So that arrow shows the difference between where we started, the reactants, and where we finished the products. That is our change in enthalpy. Okay. Our labeled y-axis can tell us that difference. Okay. From where we started to where we finished, we started at 100, we went up to 175. So that is a difference of 75. Okay. And we are going up. We are putting more potential energy into our products compared to the reactants. So this is an endothermic reaction and should have a positive change in enthalpy. Okay. Again, an endothermic reaction, anytime you have a chemical potential energy diagram where the products are higher, it's endothermic. Now, sometimes students are like, doesn't this violate the law of conservation of energy? How can you, by some miracle, end up with more energy at the end than you do at the start? Okay. Now, it's not a miracle. That energy was just taken from somewhere else. That energy was taken out of the surroundings. Okay. These chemical potential energy diagrams are for the system. Okay. The surrounding always does the opposite. Okay. So if the system gained energy, the surroundings lost energy. The surroundings got colder. Okay. And the reason they got colder is because they lost energy. Okay. That's just a bit of a highlight and recap of chemical potential energy diagrams.